Hello everyone, welcome back to my YouTube channel. In this video, I'll talk about activation functions. Activation function calculates a weighted total and then adds bias to it to decide whether a neuron should be activated or not. The activation function's goal is to introduce non-linearity into a neuron's output. A neural network without an activation function is just a linear regression model in deep learning. Since these functions perform non Since these functions perform non-linear computation on the input of a neural network, enabling it to learn and do more complex tasks. Therefore, studying the derivatives and application of activation functions also as analyzing the pros and drawbacks of each activation function is essential for selecting the proper type of activation function that may give non-linearity and accuracy in a particular neural network model. We know that neurons in a neural network work following their weight, bias, and activation function. We would change the weights and biases of the neurons in a neural network based on the output error. Backpropagation is the term for this process because the gradients are supplied simultaneously with the error to update the weights and biases activation functions, therefore enabling backpropagation. So in this video, we will talk about why do we need activation functions in CNN? What are the variants of activation function and Python code implementation of all these activation functions? And then conclusion. So why do we need an activation function? Nonlinear activation functions. Without an activation function, a neural network is just a linear regression model. The activation function transforms the input in a nonlinear way, allowing it to learn and as well as accomplish more complex tasks. This is a sample neural network. Here A1 is equal to Z1 equal to W1X plus B11. Here layer 1's vectorized output is Z1. W1 denotes the vectorized weights W1, W2, W3 and W4 applied to hidden layer neurons. X denotes the vectorized input features I1 and I2 and B denotes the vectorized bias B1 and B2. Any linear function has A1 being vectorized form. The output layer or layer 2 is as follows. Layer 2 input is Z2 equal to W2 A1 plus B2 A2 equal to Z2 A1 plus B2 A2 equal to Z2 into A1 plus B2 A2 equal to Z2 A1 plus B2 A2 equal to Z2 A1 plus B2 A2 into 2. Output layer calculation. Here, here is where we will put the value of Z1. W2 star W1 X1 plus B1 plus B equal to W2 star W1 X plus B1 of 2. For example, let's consider W is equal to W2 into W1 and B is equal to W2 star B1 plus B2. Then our Z2 function will be W star X plus B is the final result of which is a linear function once again. Even after applying a hidden layer, this observation yields a linear function. Hence, we can deduce that no matter how many hidden layers we add into neural network, all layers will behave the same way because the combination of two linear functions yields a linear function. What are the variants of activation functions? So there is linear function equation. The equation for a linear function is y equal to ax, which is a very much similar to the equation for straight line, and it goes from minus infinity to plus infinity range. Applications, the linear activation function is only used once, that is in the output layer. Second one comes the sigmoid function. The problem with the linear function is if we differentiate a linear function to introduce non-linearity, the outcome will no longer be related to the input x and the function will become constant. Hence, our procedure will not show any behavior. For example, determining the price of a home is a regression problem because the price of an apartment might be a large or little number. We can employ linear activation at the output layer. Any non-linear function at a hidden layer of the neural network is required. And the next one comes sigmoid function. It is a function that is being plotted in form of S. Formula for it is given by A equal to 1 upon 1 plus e to the power minus z. This is non-linear in nature. The value of x ranges from -2 to +2, but the y values are very highly steep. This indicates that slight changes in x will result in massive changes in y's value. It goes from 0 to 1. Then next comes tanh function. Tanh function, also identified as tangent hyperbolic function, is this is an activation function that almost always works better than sigmoid function. It is simply a sigmoid function that has been adjusted. Both are related and can be deduced from each other. Equation for tanh function can be given by fx is equal to tanh, that is 2 upon 1 plus e to the power minus 2x minus 1, or tanh is equal to 2 star sigmoid 2x minus 1, or tanh is equal to 2 star sigmoid 2x minus. And there are some uses of tanh function, that is, it is usually employed in hidden layers of a neural network since its value changes from -1 to 1, causing the hidden layers mean to be 0 or very close to it, which aids in data centering by bringing the mean close to 0. This makes learning the next layer much more straight. And then next activation function is ReLU activation. It is also short form of rectified linear unit. This is the fourth letter in the alphabet. It is most used activation method. Hidden layers of a neural network are primarily used. Formula for it is given by ax is equal to maximum of 0 comma x. If x is positive, then it returns x. Otherwise, it returns 0. Value of ReLU function can be from infinity to 0. It is non-linear in nature, which means simply by propagating errors and also having the ReLU function activating many layers of neurons. What are some applications of it? Because it includes fewer mathematical operations, ReLU is less computationally expensive than tanh and Sigmoid. Only a few neurons are active at a time, making the network scarce and efficient for computation. Simply put, ReLU function learns much faster than the Sigmoid function and tanh function. The next one comes the Softmax function. The Softmax function is a type of Sigmoid function that comes in handy when dealing with categorization issues. It is non-linear in nature, and some uses of it are like typically utilized when dealing with many classes. The softmax function would divide by the sum of the outputs and squeeze the outputs for each class between 0 and 1. Output. The softmax function is best used in classifiers output layer, where we are trying to define class of each input using probability. If one is unsure about activation functions to utilize, just select ReLU, which is broad activation function that is used in most circumstances these days. If our output layer is meant to be used for binary identification detection, then Sigmoid function is an obvious choice. Now we will be implementing Python code for sigmoid derivative function, and let's check how can we do that. So here is Python code implementation of sigmoid activation function. So what we are doing here is that we have defined a sigmoid function for our data. We are passing some random array to the function x, and then we are defining the function sigmoid. So here we have defined x array as a random value between -6 and 6, and with step as 0.01, and then we have defined values for s comma ds, that is s and derivative of sigmoid function. Then here we have plotted the graph, and then this is the graph that we will get when implementing sigmoid function and the derivative of the uh, array. So if you have enjoyed the video, please do not forget to subscribe and like the video. And there are some key takeaways from this video. That is, we have covered the basic introduction about activation function. We have discussed about softmax function, sigmoid function, ReLU function, and Tanh functions, and there is linear function as well. And we also covered some various needs to deploy the activation function. That is, when can we use which activation function, and then there comes like Python implementation of sigmoid activation function, and then there have been some different type of variant, and then we have covered various type of activation functions, and at last we covered the need for addition of non-linearity with activation functions as